Chapter 10, number 20. In Part B of Example 10.2, the compact disk was modeled as a rigid object under constant angular acceleration to find the total angular displacement during the playing time of the disk. In reality, the angular acceleration of a disk is not constant. In this problem, let us explore the actual dependence of the angular acceleration. This problem has parts A, B, and C. I will show each part by part as we work through the problem. A. Assume the track on the disk is a spiral such that adjacent loops of the track are separated by a small distance h, so that the radius r of a given portion of the track is given by r equals r initial plus h divided by 2 pi times theta, where r initial is the radius of the innermost portion of the track and theta is the angle through which disk turns to arrive at the location of the track of radius r. We start with the equation for the radius. The radius at any given time will be r equals r initial plus delta h, where delta h is the change in distance of radius. Because we assume it's a spiral, the distance the disk spins is proportional to the distance the radius moves out, or delta h. So we can express delta h as n amounts of revolutions divided by 2 pi times h. Because revolutions can be expressed as radians or as theta, we can rewrite this expression as theta divided by 2 pi times h. And switching the multiplication between theta and h, we can say h divided by 2 pi times theta. Then we can substitute for our new derived equation for delta h into r equals r initial plus delta h, where delta h equals h divided by 2 pi times theta. To get the equation r equals r initial plus h divided by 2 pi times theta. Part B. So that the rate of change of the angle theta is given by d theta dt equals v divided by quantity r initial plus h divided by 2 pi times theta, where v is the constant speed with which the disk surface passes the laser. Using the equation v equals r omega, we can solve for omega. Omega equals v divided by r, and the units of omega are d theta dt, which equals v over r. Now, using the answer from part A, we can plug that into d theta dt equals v divided by r, which gives us d theta dt equals v divided by r initial plus h divided by 2 pi times theta. Part C. From the result in Part B, use integration to find an expression for the angle theta as a function of time. Using the equation for Part B, we will use the technique of separation of variables to solve for the equation for theta. This is our initial expression from Part B. I will show each slide, and if need be, hit pause so you can review the steps of this problem. Okay, now that we know a correct expression, we will manipulate it to make it look good. Oh, and note, we use a positive symbol for the radical to get the positive angle. And this will be our final answer for Part C. Part D. From the result in part C, use differentiation to find the angular acceleration for the disk as a function of time. This is our initial expression for part C. Again, I will show each slide individually, and if need be, hit pause so you can review each step of the problem. Using a little simplification, we find that we see that our final result is this expression. And because we see a t here, that means it's dependent on time, which signifies that its acceleration is not constant.